Hello, in this presentation we are going to talk about algorithms for unsupervised learning, and especially about a method which is called expectation maximization, which is used for estimating the parameters of probability distributions, especially when some of the random variables involved in these probability distributions are hidden or latent. So in this talk, I will cover k-means, which can be seen as a special case, a very special case of mixture of Gaussians, and both methods can be understood from the expectation maximization approach. So in k-means, we want to solve the clustering problem. In the clustering problem, we are given a training set. In this case, we have m vectors, m input vectors, x, and each of these vectors is in dimension n. Since we are talking about unsupervised learning, we don't have the labels of these input vectors. And the goal behind k-means is to group these input vectors into a few cohesive clusters. And this is an unsupervised learning problem, as I mentioned before. So the k-means clustering algorithm is as follows. You initialize some cluster centroids. In this case, we are considering that we will initialize with k centroids. And when we decide about the value of k, we are making a hypothesis that there is only k clusters in our data, and this is why this is called k-means. We are making the guess that we will have only k groups of points in our data set. So we initialize these k centroids or means, and of course, if our data set contains input vectors of size n, our k centroids should have also n dimensions. So once we have initialized the centroids, we get into the main loop of the algorithm. The main loop contains two steps. In the first step, for every training example I, for every input vector x, we need to assign a cluster or the label of one of the clusters. So here, assume that this C here is a vector in one dimension, and you will assign to each position I the label of the centroid that is the closest one to the input vector I. So you will visit each of the points in your data set, and you will check which of these k-means is the closest one, and closest one is measured using the distance between two vectors, the Euclidean distance between two vectors. So you will visit each of these points, and you will compute the distance to each of the means. And if, for example, the mean 2 is the closest one to some vector I, then this label 2 will be assigned to the position I in the vector of centroids. And in the second step, once we have assigned a centroid or a mean to each of the points in our data set, we need to recompute these centroids, and we do that simply by computing the average of all of the points that were assigned to the same centroid J. So suppose that you are talking about 3 centroids in total, so k equals 3. In this step, you will take first centroid 1, and you will check how many of the total number of input vectors were assigned to cluster 1, to centroid 1, and you will compute the average of those vectors. So this is the formula. This is what this formula is saying. Compute the average of those vectors that were assigned to cluster 1. And you will do that for cluster 2, centroid 2, and centroid 3 in this example. And you will repeat this. You will reassign the centroids and then update the mean or the average of the vectors until you notice that the assignation or the assignment of these input vectors is not changing anymore. So the inner loop of the algorithm executes these 2 steps, assigning each training example xi to the closest cluster centroid mj, and moving each cluster centroid to the mean of the points assigned to it. So k is the number of clusters, as I said before, and usually we don't know how many clusters we will have, so we need to run experiments with different values for k. The clusters, the cluster centroids m, muj, represent our current guesses for the positions of the centers of the clusters. We could choose k training examples randomly and set the initial cluster centers to be equal to the values of these k examples. Other initialization methods are also possible. So the simplest one is to take your input data set. Suppose that you are given 1000 input vectors, and if you are going to experiment with k equals 3, so you are assuming that there are 3 clusters, then you simply select randomly 3 of your 1000 input vectors, and these 3 that were selected, you can assign them as the initial centroids. Of course, this is not true, but this is a way to initialize, to give an initial value to these centroids. And as the algorithm keeps assigning centroids and updating the means, the algorithm will find or discover the correct centroids of these points. But as it says here, there are other ways to initialize the k-means algorithm. So here is an example where we can see what is going on with this algorithm. So first, you are given a set of input vectors. All the points are painted here in green because it means that we don't have labels for the points. And here in this experiment, we are assuming that there are 2 clusters, and in this case the centroids were initialized randomly, so they just selected 2 points into this square, and they say this centroid is going to be called the red centroid, and this is the blue centroid. So this is the initialization. After the initialization, you run the first step of the algorithm, which is visiting each of these green points and calculating the distance to each of the centroids, the red and the blue. And for example, in this case, this green point is closer to the red point than to the blue one, so it was painted as red. And for example, this point here is closer to the blue, so it was painted as blue. So this is the first step, the first assignment of centroids to each of the points in your data set. In the second step of the algorithm, you check all the points that were assigned to the centroid red, and then you compute the average or the mean of these vectors, and in this case this cross here is indicating the location of the centroid. You do the same with the blue points, and here you can see the centroid of blue points. Then again you assigned the points to the closest centroid. By doing that, now you will see that all these points here are closer to the blue centroid, and that's why these red points here they become blue. And the same happens with these cloud points, and these two blue points now become red because they are closer to the red cross than to the blue cross. Once you have reassigned these centroids, you recompute or update the means, and this is the updated value of x of the blue cross and of the blue red, the red mean. So at this point you can see that the algorithm has already converged, because it has already found a good estimation of the centroid. So the idea behind these algorithms, remember that we were talking about unsupervised learning, is to try to find some structure in the data. And in this case we have found that there are two kinds of data, two kinds of points that maybe we don't know what this red color means or what this blue color means in the real world application. But if we are given a new point, then we can compute the distance to the red centroid and to the blue centroid. And if it is closer, for example, to the red cross, we will say, I don't know what this point means, but it belongs to this group. And later, if you can label at least one of these red points, then you can assume that all the remaining red points are of the same type, so they have the same label that was given to the point. So there are many applications of this algorithm. Here is a application to images, and here to the left you see an image, and to the right you see the same image, but we have clustered the pixels of the image, taking into account the color of each of the pixels. So if you remember, you can represent each of the pixels as a vector in dimension 3 that will contain the amount of red, green and blue that pixel contains. So if you consider each of these pixels as vectors or points in dimension 3, you can run k-means to try to group all the pixels in this case into two groups, and all those pixels that are similar, considering that you can have only two groups, they were assigned the pixel, the color pixel that was the average of all those pixels that were the most similar between them. So if you run k-means over this image, you will get this result with k equals 2. If you increase the number of means, in this case k equals 3, then you will get this image as a result. And if you keep increasing the number of pixels, you will get a better representation of this image, of the original image. So one application of this is that you can simply detect how many colors are needed to represent the original image for a specific application that you would need, and then if you can reduce the number of colors that are enough to represent your image, you can reduce the amount of information needed to represent that image. So in this case, maybe for a specific application, representing the image only with 10 colors will be enough, and then you will be reducing the amount of information needed for storing this image. Here is another example with a different image with 2 means. This is with 3 means, and finally with 10 means. So the k-means algorithm is guaranteed to converge in a certain sense. So let us define this function, which is called the distortion function. We are calling this function j, and it's a function of z, which is the vector of centroid assignments, and the mu, which will be all the centroids, and here m is the total number of points that we were given, and this norm will represent the Euclidean distance between xi and a given centroid. So given that you have finished running k-means over some data set, you can compute this number, which is the sum of the distance from each of your points to the centroid that was assigned to that point. And this sum is a metric which will tell you, given 2 different clustering schemes, which of these 2 schemes is the more compact. And this could be used for deciding which is a best solution of the clustering for you. Now this is like the simplest distortion function that you can think of, just summing for every point the distance to its corresponding centroid, but there are some others that can be used depending on the application. So in theory, it is possible for k-means to oscillate between a few different clusterings that have exactly the same value of j, but this almost never happens in practice. And the reason is that this distortion function is a non-convex function, so it means that it has more than one minimum point. So the algorithm can get stuck in some local minimum. However, very often these k-means will work fine and will get a good clustering scheme. If you are worried about running this and getting stuck in bad local minima, usually what you do is simply you run many experiments with different case values, and even with the same k value you reinitialize the algorithm with different centroids, just to make sure that the clustering solution that you are getting is the best one for your application. So this k-means is a very intuitive and very simple algorithm for finding clusters of points. And in the case of this distortion function, let me go back to show it. If you are running k-means in datasets where your input vectors are in dimension, let's say dimension 2, well, visually you can see, you can have an idea of how many groups or clusters seem to be existing in that data set, because it is a 2D plot that you can very easily generate, or even in a 3D plot with vectors in 3 dimensions, you can plot them. But if you are considering points that are in dimension 10 or 20, then you cannot plot it and visually find this structure in this data if if it looks to be 3 or 5 clusters. So this distortion function is the only way that you have to compare different solutions. And as I said before, there are other ways to define these distortion functions. So a typical way to apply k-means is to define different distortion functions. You run the clustering and you write down the metric given by each of your distortion functions, and then you will accept the solution, the best solution, to be that one that maximized most of the distortion functions that you are using as your metrics. Now, k-means, as I said, is an unsupervised learning method, and it is quite old. It was proposed like 60 years ago, but even though it is old, it is very simple, and in practice is most of the time is the best way to try to find structure in data that it is not labeled. There have been many variants of this method, but usually the standard version is the best way to go. You will see when we study mixture of Gaussians, which is another method for unsupervised learning, that mixture of Gaussians is very similar to k-means, in the sense that you have 2 steps where you have to assign centroids and then recompute the value of some parameters. In this case, in k-means, you assign each of the points in your data set to only one of your centroids. You will see in mixture of Gaussians that in mixture of Gaussians you make a soft assignment, so each of your points will belong to a certain extent to each one of the centroids that you are considering. And also here in k-means you are recomputing each time the mean or the average of the centroids. It's only one parameter that you need to re-estimate or recompute. In mixture of Gaussians, you will see that there are 2 parameters that you need to recompute, which are the mean and a covariance matrix. So I mentioned this now, so when we start studying mixture of Gaussians, you can try to make a connection with this algorithm. Both methods can be analyzed as applications of the more general method that we're going to study next, which is the expectation maximization method.